In this video, we'll be going over the 2007 AP Calculus exam. In question 1, let R be the region in the first and second quadrants, bounded above by the graph of y equals 20 over 1 plus x squared, and below by the horizontal line y equals 2. As you can see on the right here, I've also included a sketch of that graph from Desmos. Obviously, if you're actually taking the test, you wouldn't have Desmos, but you would have your graphing calculator. And I also have the horizontal line y equals 2 here. Let's go ahead and sketch that real quick. Remember, y equals 2 is a horizontal line. Actually, wait, I can just do this. Something like that. Okay, that's y equals 2. Okay, so in part A, we're asked to find the area of R. So R is the region in between the line and the curve, so it would be this region right here. That is R, that's what we want to find the area of, okay? So whenever we want to find the area of a region like this, we have two intersection points here that we need to figure out. That's always the first step, finding the intersection points. And how do we figure those out? Well, we're simply going to set these two equations equal to each other. So for example, here we have, this is y equals 20 over 1 plus x squared, this is y equals 2, so we'll set those two equal to each other to get these 2 points. So we'll set 20, actually let's do it in this color. Just do white. 20 over 1 plus x squared equals to 2. And then if you solve this for x, you will get x equals negative 3 and x equals positive 3. So here we get x equals negative 3. Here we get x equals positive 3. Okay? Now we can simply use the formula, and the formula for finding the area is the integral from a to b of the top minus the bottom dx. What is top and what is bottom? Well, top, actually I can say here, top is the top curve and this is the bottom curve. So it's like the top bound and this is the bottom bound. And then a and b are the x-coordinates of the left intersection and the right intersection, respectively. So in our case, a is negative 3, b is positive 3. The top curve is this one, which is 20 over 1 plus x squared, and the bottom curve is this one, which is y equals 2. So plugging all that in, we have the integral from negative 3 to 3 of 20 over 1 plus x squared minus 2 dx. If you evaluate this in your calculator, you will get 37.962, and that is our answer. This is a two-part question, one part for the integrand, one part for the answer. Part B, find the volume of the solid generated when R is rotated around the x-axis. Okay, so whenever you see these kind of problems, you always want to, the first thing you want to do is identify your radius or your radii. So what it's going to look like is that you're going to look at where you're rotating from. So here we're rotating about the x-axis, right? That's this black line in the bottom here. And what we want to do now is we want to find the distance from the thing that we're rotating around to each of our curves. In this case, we have two different curves. We have y equals 2 and we have y equals 20 over 1 plus x squared. So we're going to find the distance from the x-axis to each of these two curves. So the first one is from the x-axis to y equals 2. That's this distance here, right? And I'm going to call that, I'll say it's called little r1, okay? And then notice that no matter where you are on the x-axis, no matter what your x value is, this distance is always going to be 2, right? If it's here, the distance is still 2. So we can say that r1 is a constant value of 2. And then the other hand, r2, that's going to be the distance from, let me move it over a bit actually. If it's distance from the x-axis to the top curve, right? And notice that's going to change as x changes. That's basically what that is. It's the height of that second of this function, right? So it's basically like the y value of that function is the height of this line. So r2 is this height, which is 20 over 1 plus x squared. That's the y value. So r2 is 20 over 1 plus x squared. Now all we have to do is plug these into our formula, which is the integral from a to b of r2 squared minus r1 squared dx, and then multiply that by pi. Okay, we see here that a and b are still x equals negative than x equals 3. R2 is this, R1 is this. So all we gotta do is plug this in. So in our case, we'll have pi integral negative 3 and 3. R2 is 20 over 1 plus x squared. And then R1 is 2. Evaluating this gets you 1871.190. And obviously you do that in your calculator. Okay, so for points, this is 2 points for coming up with the integrand, 1 point for coming up with the answer. Part C. The region R is the base of a solid. For the solid, the cross-sections perpendicular to the x-axis are semicircles. Find the volume of the solid. So basically, if you're not sure, what this question is asking is that this purple region R, it's basically, you're basically drawing a bunch of semicircles using this region R. So I'm drawing a couple of semicircles here. I'll draw another one here. So you're basically drawing an infinite number of semicircles, and all those semicircles together are going to create this like 3D shape, and you're basically asked to find the volume of that shape. Okay, so the first thing we want to do is actually figure out the diameter of these semicircles. Okay, so let's focus in on this one here. If you'll notice, the diameter is actually the difference between, the distance between the first and the second function. So it's the difference between y equals 2 and y equals 20 over 1 plus x squared. Right? So we can actually write down the formula for the radius, or for the diameter of the semicircle, as this y-coordinate minus this y-coordinate, which is 20 over 1 plus x squared minus 2. If you want to think about it another way, this total distance from the x-axis to this red graph is 20 over 1 plus x squared, but that also includes this distance 2, so we need to subtract that to just get this blue distance. Either way, you'll arrive at this as your diameter for the semicircle. Okay, now we want to find the area of one semicircle, right? So for this, if this is the diameter of the semicircle, right, to find the area, remember the formula for the area of a semicircle is 1/2. I'm doing a different color actually, just to the diameter. Sorry, the area of a semicircle is 1/2 pi r squared, where r is the radius. Notice here we have the diameter. So first thing we need to do is turn this into the radius by dividing by 2. If we divide by 2, we'll get 20 over 1 plus x squared minus 2 over 2. Right, that's our radius. And we'll take this, and then we'll plug it into here. Okay, that's going to give us 1/2 times pi times 20 over 1 plus x squared minus 2 over 2 squared. Okay, so this is the formula for the area. Now I want to find the volume. Okay, to find the volume, all I have to do is I have to take this and I have to integrate it across my region. So here my region is going from x equals negative 3 to x equals positive 3, so I just need to integrate my formula here from negative 3 to 3. Okay, so we'll integrate from negative 3 to 3, and I'll simplify this a bit. I'll just write pi over 8, and then 20 over 1 plus x squared minus 2 squared dx. And then if you were to evaluate this in your calculator, you would get 174.268. Okay, there we go. This was a 2-point question, 1 point for the integrand, 1 point for the answer. And for this entire first question, if you had the correct limits, you would get an extra limits point. Okay, that's the end of question 1. Let's move on to the next one. The amount of water in a storage tank in gallons is modeled by a continuous function on the time interval from 0 to 7, where t is measured in hours. The rates are given as follows. The rate at which water enters the tank is f of t. The rate at which water leaves the tank is g of t. The graphs of f and g, which intersect at t equals 1.617 and 5.076, are shown in the figure above. At time t equals 0, the amount of water in the tank is 5,000 gallons. Okay, so I think first what we should do is we should label these intersection points. So this is 1.617, and this is 5.076. Next, we should label the graphs. So f of t is this continuous function, which is this one here. This is f of t. And then this piecewise function here is two straight lines. That's g of t. Okay? So, looking at part A, how many gallons of water enter the tank in the time interval from 0 to 7? Round your answer to the nearest gallon. Okay, so if we want to look at how much water is entering the tank, we should probably be looking at f of t, right? Because that's telling us the rate at which water enters the tank. So if we want to find out how much water entered the tank over an extended time interval, we need to take f, which gives us the rate at which that's happening, and we need to integrate it across whatever time we want. So in our case, we're going from 0 to 7, so what we should do to figure out how many gallons of water enter the tank from 0 to 7 is we should take our function that's giving us the rate at which that's happening, and we should integrate it from 0 to 7. That's going to give us the total amount of water, f of t dt, and then since we know what f of t is, that's just 100 t squared sine of the square root of t. That's going to be equal to, if you put this in your calculator, it'll be 8,264 gallons. And also you can know that the units are gallons because they ask you how many gallons of water enter the tank. This was a two-part question, one part for the integrand, one part for the answer. Part B, from 0 is less than or equal to t is less than or equal to 7, find the time intervals during which the amount of water in the tank is decreasing. Give a reason for your answer. So I'm going to figure out where the water in the tank is decreasing. If you just think about this logically, if you want the amount of water in the tank to be decreasing, that means the amount of water going out has to be greater than the amount of water coming in, right? For the amount of water to be decreasing. And then, well, let's see, the amount of water coming out, that's given by g of t, that's the amount of the rate at which the water is leaving the tank. So g of t, and the amount of water coming in, that's given by f of t, right? The rate at which water enters the tank. So to figure out when the amount of water is decreasing, we need to figure out where is g of t greater than f of t. So if we look over here on our graph, we need to figure out where the straight lines are above the curves. Okay? So if we just go and sketch along here, here you can see in this interval, here, actually let me do it here. So in this time interval, you can see that f of t is under g of t. In this time interval, you can see that g of t is under f of t. And then in this time interval, you can see that g of t is above f of t. And then finally, from here on, f of t is above g of t. Okay, so you can see in these two green segments, here and here, g of t is above f of t. Okay, so those are the segments where the amount of water in the tank is decreasing. So let's write that down. Okay, so this time is 0, this time is 1.617. So 0, 1.617. And this time interval, so this point where g of t switches from here to here, if we look at our piecewise function, it switches at t equals 3. So the starting time is 3, and then it ends right here, it ends at this intersection point, which is 5.076. Like that. And then for our reason, we'd say because something along the line, just because g of t is greater than f of t for these values of t. Okay, so the amount of water going out is more than the amount of water coming in. Okay, that's your answer. This was again a two-part question, one part for the answer, one point for the explanation. From t between 0 and 7, at what time t is the amount of water in the tank greatest? To the nearest gallon, compute the amount of water at this time, and of course justify your answer. Okay, so I think a good step for this problem would to figure out when the amount of water in the tank is greatest is we figure out a function that gives us the amount of water in the tank as a function of time, and then we try to maximize that function. Okay, so let's call a function w of t as the amount of water that's in the tank. Okay, so we know initially there's 5,000 gallons of water in the tank, right? Because at time t equals 0, the amount of water is 5,000. So that's the amount that we're starting off with. And then remember from part A, we said that the amount of water coming into the tank is the integral of f of t from 0 to whatever time interval we want. Okay? And then we also know that the amount of water leaving the tank, therefore, would be the integral from 0 to t of g of t dt. But since it's the water leaving the tank, we should subtract it. Okay, so here's how much we're starting with. Here's how much water goes in, and then here's how much water goes out that we're subtracting because it's going out. So this will tell us how much water there is in the tank at a certain amount of time. Okay, and we want to maximize this function. So what we'll do is we'll take the derivative of it and set it equal to 0. Okay, so if we take w prime of t, that's going to be, because this constant is going to go away. This, by the fundamental theorem of calculus, remember the fundamental theorem of calculus says that if you take the derivative of an integral, they kind of just cancel out and you just get f of t left over. Okay, so using that here, if we took the derivative of this, we just get f of t. Here, we just get minus g of t. Okay, so we want to figure out when does this switch from, if we want the amount of water to be the maximum, then we want the derivative to be switching from positive to negative, right? Positive to negative if at a maximum. So we want g of t to become greater than f of t. Where does g of t become greater than f of t? Because that's when the derivative will switch from positive to negative, right? Because if we're subtracting a bigger number, it's going to be negative. So we want to figure out where g of t becomes greater than f of t. That's when it's going to start being negative, right? That's when it switches from positive to negative. So where does g of t become greater than f of t? Well, we can look up here and see where that switch happens. So here, f of t is less. So here g of t is greater. Here g of t is less. And then here at time t equals 3, we notice that g of t switches from being less to being more. So at this point, the amount of water is a candidate for being the maximum, because that's when g of t switches to being greater than f of t. So that's our candidate point. I'm going to read it in white actually. Candidate point at t equals 3. Okay, and then here it's still g of t still greater, and now f of t is greater. So in our function, t equals 3 is the only point where g of t switches to be greater than f of t all of a sudden. Okay, so to figure out the absolute maximum now, we need to make a table. Okay, so in our table, we'll have all our candidate values. So our candidate values are going to be t equals 3 from before, and then both of our endpoints. In this case, it's going to be t equals 0 and t equals 7. Okay, and then we need to figure out what the value of w of t is at those points. Okay, so w of t. So what is w of 3? Well, if we go up to w here, we just plug in 3 for t here in these two places. That's going to be 5,000 plus the integral from 0 to 3 of f of t dt minus the integral from 0 to 3 of g of t dt. If you put this in your calculator, this comes out to be around 5,126.591 gallons. I'll say g. Time t equals 3, we'll have 5,000 plus. Now for both of these integrals, the limits are going to be 0 and 0, right? And then for any integral, if you have the same limits here, it's just going to equal 0. So these two are just going to go away, and we're just left with 5,000. T equals 7, we'll plug in 7 instead of 3 here, so we'll get 5,000 plus integral from 0 to 7 of f of t dt minus integral from 0 to 7 of g of t dt. if you plug this in your calculator, you will get 4,513.807 gallons. So we've shown that out of these three, these are the only three options for the absolute maximum. And then since this is the greatest out of all these three, this must be the absolute maximum amount of water in the tank. So let's go back and look at what the question was asking us. It's asking what time t is the amount of water in the tank the greatest. Well, that's going to be a time t equals 3, right? And then they're also asking us what is the amount of water at this time to the nearest gallon. Well, taking this to the nearest gallon, it's going to be 5,127 gallons, okay? So for your answer, you'd say, okay, at time t equals 3 hours, the amount of water in the tank is the maximum. The maximum value is 5,127 gallons. And then this is actually kind of your justification here, because you're showing you're identifying all of the possible candidate values and then testing them each out to figure out which one is the actual greatest. So this would count as your explanation. So in terms of points, we have 1 point for identifying t equals 3 as your candidate value. We have 1 point for testing it out, and then 1 point for coming up with the correct answer. That's the end of question 2. Functions f and g are differentiable for all real numbers, and g is strictly increasing. The table above gives values of the functions and their first derivatives at selected values of x. The function h is given by h of x is equal to f of g of x minus 6. Part A, explain why there must be a value r, where r is between 1 and 3, such that h of r equals negative 5. Okay, so a good step here to start off might be plugging in 1 and 3 into h. Okay, so let's find h of 1. H of 1, we'll plug in 1 here, so we'll get f of g of 1 minus 6. Okay, well, what's g of 1? If we go to our table, g and 1 equals 2. So this is f of 2 minus 6. What's f of 2? Well, f of 2 is 9. This equals 9 minus 6, which is 3. Similarly, let's find h of 3. Okay, so this is going to be f of g of 3 minus 6. What's g of 3? Is equal to 4. That's f of 4 minus 6. Well, what's f of 4? F of 4 is negative 1. Negative 1 minus 6, which is negative 7. Okay? So now they want us to explain why there must be a value r, where r is between 1 and 3, such that h of r is negative 5. Okay, so first of all, we know the functions f and g are differentiable. That must mean that h is continuous, right? Because it's made up of f and g. So if h goes from 3 to negative 7, so if we were to, like, for example, just draw like a random sketch of h, and we know it starts at 3 and does something and it goes to negative 7, then it must pass through negative 5 on the way there, right? Because it's a continuous function. That isn't technically a function. If it's like, it must pass through negative 5 somehow along the way there, right? So we can say that because it starts at a value that's above negative 5 and it ends at a value that's less than negative 5, there must be some value where it's equal to negative 5. Okay? So our explanation will be, since h of 3 is less than negative 5 is less than h of 1, right? H of 1 is 3. And so negative 5 is in between those values, and h is continuous. H is continuous. There must exist some, I'm just going to say this, I'm not going to write it out, but there must exist some value of r, where r is between 1 and 3, such that h of r equals negative 5. Okay, that's going to be our explanation there. So this is a 2-point question. 1 point for finding h of 1 and h of 3, like this, and another point for your explanation of why there must be a value of r. Part B. Explain why there must be a value c, where c is between 1 and 3, such that h prime of c is equal to negative 5. Okay, so this is going along, it looks very similar to part A, but now notice they're asking about h prime of c, not h of something, right? So since we're looking at the derivative, we should probably find the average slope between 1 and 3 for c. Okay, so remember the formula for slope is f of x2 minus f of x1 over x2 minus x1. You might also think of it as y2 minus y1 over x2 minus x1, right? So we're going from 1 to 3. So this is going to be h of 3 minus h of 1 over 3 minus 1. And we already found h of 3 and h of 1 in part A. It's going to be negative 7 for this, 3 for this, over 3 minus 1 is 2, so it's equal to negative 5, okay? Notice that it's exactly equal to h prime of c. So now, I want you to think about the mean value theorem now. If you remember, the mean value theorem says that if you have a continuous function, right? Let's say it looks like this. If you know the average slope between 2 points, then the derivative must be equal to that average slope somewhere in between those 2 points. So for example, in this graph here, the average slope here is equal to the derivative maybe somewhere like here. So using the mean value theorem, here, since we know that the average slope between 1 and 3 is equal to negative 5, there must be some value for c that's in between 1 and 3. Since we know that the average slope between 1 and 3 is negative 5, there must be some value of c that's in between 1 and 3 such that the derivative is negative 5, right? We're just using the mean value theorem. So what you'd say now, I'm not going to write it out again, is that since h is continuous and differentiable, by the mean value theorem, there exists some value c between 1 and 3 such that h prime of c equals negative 5. And you're going to want to show this work too, because this is a 2-point question. 1 point comes from doing in this and finding the average slope and showing that it's equal to negative 5. And the second point for your explanation using the mean value theorem. Part C. Let w be the function given by w of x is the integral from 1 to g of x of f of t dt. Find the value of w prime of 3. Okay, so since we know that w of x is equal to this, w prime of x must be the derivative with respect to t of integral from 1 to g of x of f of t dt. Oops, that's not what I meant. I meant ddx, because here's respect to x. Okay, so here's w prime of x, right? Now for this part here, we need to use the fundamental theorem of calculus. Remember I said previously that the fundamental theorem of calculus says that the derivative of the integral from a number a to x, a can be anything, of f of t dt equals f of x, right? So here, we're just going to apply that, and we're going to say w prime of x is here, if we do that, we're just going to get f of g of x. But now since this is not a number, it's not just like x, it's a function, we need to use the chain rule here and take the derivative of it. Okay? Remember, use the chain rule whenever the thing that you're doing, see if you're taking x and plugging it in here, here we're taking g of x and plugging it in here. Anytime that the thing you're doing the action to is not just x, it's like f of x or g of x or whatever, then you need to take the derivative of it by the chain rule. So here, since it's not just x, it's the function f of x, we're taking the derivative of it by the chain rule. So now here's our function for w prime of x. Now to find w prime of 3, all we got to do is plug in 3. F of g of 3 times g prime of 3. Okay, let's look at our graph. So g of 3 is 4, and g prime of 3 is 2. So this is going to be f of 4 times 2. And what's f of 4? Let's see, f of 4 is negative 1. So that is negative 1 times 2, negative, so you can squeeze in there, negative 2. Okay, that's our answer. This was a 2-part question. 1 point for correctly using the chain rule, 1 point for the correct answer. Part D. If g negative 1 is the inverse function of g, write an equation for the line tangent to the graph of y equals g negative 1x at x equals 2. This is an inverse function problem, right? So whenever they say write an equation for the tangent line, always the first thing you should do is you should write down 2 words, point and slope. Okay, you need to find a point to write the tangent line, and you need to find the slope. Okay, so since they want the tangent line at x equals 2, our point is going to be 2, comma, and we have to plug in 2 into here to get the y value, right? It's going to be g inverse of 2. Okay, so this is the point. To figure out what g inverse of 2 is, we need to look at g of what equals 2. That's going to give us g inverse of 2. If we look at a function for g, we see that g of 1 gives 2, right? So this question mark is equal to 1. So that means g inverse of 2 is equal to 1. So the point is 2 comma 1. Okay? And now we need to find the slope. So the slope, remember that since y is g negative 1x, the slope is going to be g negative 1 prime of x. Okay? And now to solve this, you need to know the formula for the inverse derivative. So if you have just like a general function f of x, and you want to find f negative 1 derivative of x, that's going to be 1 over f prime of f negative 1 of x. Okay, that's the formula that you got to know. So here we can figure out the slope by using this formula, and we'll just replace f with g. So let me make it a bit smaller. There we go. So we'll just replace f with g here. So g negative 1 prime of x is 1 over g prime of g negative 1 of x, okay? So now we want to figure out the slope at x equals 2, right? So to figure that out, g negative 1 prime of 2 is going to be equal to 1 over g prime of g negative 1 of 2. Okay? Well, what's g negative prime of 2? Well, we set up here that's equal to 1. So this is actually just 1 over g prime of 1. What's g prime of 1? Look at the table, g prime 1, 5. This is just equal to 1 over 5. Okay? So the slope is 1 over 5. So now we have our point, we have our slope, we can write our equation now. All we need to do is remember the point-slope form, which is y minus y1 equals m times x minus x1, where m is this, and x1 comma y1 is 2 comma 1. Okay, so plugging that in to get our final answer, we'll have y minus, so y1 is 1, equals m is 1/5 times x minus, and then x1 is 2. Okay, there is our answer for part D. And then in terms of points, this was a 3-point question. 1 point for correctly figuring out that g inverse of 2 is equal to 1. Another point for successfully taking the derivative to find the slope. And the third point for putting everything together to get the equation of the tangent line. That was the end of question 3. Question 4. Particle moves along the x-axis with position at time t given by x of t equals e to the negative t sine of t for t between 0 and 2 pi. In part A, we're asked to find the time t at which the particle is farthest to the left, and we need to justify our answer. Okay, so when they ask us when the particle is farthest to the left, that right there is just a keyword. That means they want the absolute minimum, right? Because usually when we think of directions, we say right is positive and left is negative. So if they want the farthest to the left, they want the lowest value of the position. So they want the absolute minimum of the position. And when we have a function for the position here, so basically they're just asking us to find the absolute minimum of this function. So we can basically reword part A to say find the absolute minimum of x of t. Okay? So how do we find that? Well, when we want to find the absolute minimum, we're looking at two things. First, we're looking at the endpoints. And then we're also going to be looking at relative minimum. Okay, so we'll find all the endpoints and we'll find all the relative minimum. Okay, so we'll start the relative minimum first because it's harder. Okay, so to find the relative minimum, we're going to take the derivative of x of t and set it equal to 0. Okay, so to find that, we'll do x prime of t, and then since we're multiplying two things together, we're multiplying this e to the negative t and the sine of t. We'll use a quick product rule. We'll get negative e to the negative t sine of t plus e to the negative t cosine of t. Okay, now in a new line, I'll set this equal to 0 because when we want to find the relative extrema, we set this equal to 0. Okay, we set it equal to 0. Now I can factor out an e to the negative e to the negative t, and I'll get cosine t minus sine t equals 0. Okay, so now this part here, this can never equal 0, right? If you look at a graph of e to the x, it's like this. So that's not going to work. So if we want this to equal 0, the only option is that this equals 0. So if cosine t minus sine t equals 0, then I can take the sine t, I can add it over here, and I'll get cosine t equals sine t. Now, when is this true? Well, it's true when cosine and sine have both the same signs. So we're looking in the first and third quadrant of the unit circle. That means we're going to have pi over 4 and 5 pi over 4 for the values of t. That'll make this equal. Okay, so these are the relative minimums. And then now what we need to do is we need to find the endpoints. Okay, by the way, if you're asking, could this be relative maximum as well? Technically, you don't really care to find. We'll deal with that as it appears. You could check these with like the timeline thing, and you like put pi over 4 there, and you test a number here and a number here. But it's not really required because in the process of finding the absolute minimum, will knock out all the other stuff. Okay, so we found the relative. I should say relative extrema. Let me change that. Relative extrema. That's a more accurate way. So we found the relative extrema. Now we need to find the endpoints. Well, it kind of gave us the endpoints right here. It's just 0 and 2 pi. So the relative extrema are pi over 4 and 5 pi over 4, and the endpoints are 0 and 2 pi. So these are the 4 possible values for the absolute minimum of f of x, or sorry, x of t. My bad. So what we'll do now is we'll make a little table. We'll make t, and we'll make x of t. Okay, so we'll put in these 4 possible points: 0, pi over 4, 5 pi over 4, and 2 pi, and we'll plug each of these into x of t. Now remember, x, let me do it in a different color actually. Remember that x of t equals, what was it? It is e to the negative t sine of t. Okay, e to the negative t sine of t, like that. So if we plug in 0 here, we'll get e to the 0, which is 1, times sine of 0, which is 0. Then we'll get, for pi over 4, we'll get e to the negative pi over 4 times the sine of pi over 4. Remember, since the sine of pi over 4 is positive, and this is always positive, x of pi over 4 is going to be greater than 0. Now if we plug in 5 pi over 4, we'll get e to the negative 5 pi over 4, and then sine of 5 pi over 4. Now 5 pi over 4 is in the third quadrant. It's going to be, the sign of that is going to be negative, so a negative times a positive is a negative, so this is going to be less than 0. Finally, if you plug in 2 pi, sine of 2 pi is going to be 0, just like sine of 0 is 0. So x of 2 pi is going to be equal to 0, so this is 0. Now, since we want the absolute minimum out of these 4 values, this is the only one that's less than 0, so this is going to be our absolute minimum. Okay, so they asked us, when is the particle farthest to the left? Well, the particle is farthest to the left at t equals 5 pi over 4. This kind of table here is our justification. Okay, so you'd say, I don't want to write it down now, but you'd say the particle is farthest to the left when t equals 5 pi over 4. You get 4 points for this question, actually, my bad. You get 1 point for successfully taking the derivative of x of t, another point for setting it equal to 0, a third point for your answer of 5 pi over 4, and the 4th point for an explanation. In our case, this table is our explanation. Okay, let's look at part B. Part B. Find the value of the constant a for which x of t satisfies the equation a x double prime of t plus x prime of t plus x of t equals 0 for t between 0 and 2 pi. Okay, so just a reminder from part A, we said that x prime of t equals negative e to the negative t sine of t plus e to the negative t cosine of t, right? That was from part A when we set this equal to 0 later on, right? But here we want to find the second derivative, so we'll take this and we'll take the derivative of it, x double prime of t. So we'll start with this part here. We use the product rule here. We'll get, so the negatives will cancel out. We'll get positive e to the negative t sine of t plus, or no, rather minus e to the negative t, oops, I'm making so many mistakes here, cosine of t. So this part is from here, okay, plus a negative e to the negative t cosine of t minus e to the negative t sine of t. That part came from here. Okay, so now that we found the second derivative, let's simplify this a bit. Okay, notice we have an e to the negative t sine of t, and then here we have a minus e to the negative t sine of t. So these two things will cancel out. Okay, and now we're left with negative 2 e to the negative t cosine of t. Okay, now we have this equation, right? A x double prime of t plus x prime of t plus x of t equals 0. What I can do now is I can actually just substitute my x prime of t, x double prime of t, x prime of t, and x of t into that equation. So a times x double prime of t is going to be a times negative 2 e to the negative t cosine of t plus x prime of t. Remember from part A that was e to the negative t, and I'm simplifying this a bit here, negative sine of t plus cosine of t, and then plus x of t, which is e to the negative t sine of t, and this is equal to 0, right? So now we'll simplify this a little bit more. We'll distribute. We'll get negative 2a e to the negative t cosine of t minus e to the negative t sine of t plus e to the negative t cosine of t. Right here I just distributed the e to the negative t into both of those, and then plus e to the negative t sine of t equals 0. Cool, now what can we do? Well, similar to what we did before, we have a negative e to the t sine of t, we have a plus e to the t sine of t. These both can cancel each other out and go bye-bye. Bye-bye. And then we're left with negative 2a e to the negative t cosine of t plus e to the negative t cosine of t equaling to 0. Okay, now we'll factor out an e to the negative t cosine of t from both sides. I'll get e to the negative t cosine of t times negative 2a plus 1 equaling 0. Okay, now if we want to find the value of a, we're going to focus on this part here, right? Because they asked us, remember, what value of a will make this thing equal to 0, right? So what we'll do is we'll take this and set it equal to 0. We'll get negative 2a plus 1 equals 0, subtract 1, negative 2a equals negative 1, negatives will cancel, a equals 1/2. Okay, that's the answer to this question. A is equal to 1/2. And in terms of points, this is also a 4-point question. You get 2 points for successfully finding the second derivative. You get 1 point for plugging everything into the equation like we did here. And then you get the final point for the correct value of a, which is 1/2. That concludes question number 4. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius is modeled by the function r of t, where t is in minutes. R is concave down. That's something crucial. I actually want to highlight that to remember it. The table gives values of r prime of t, and then at t equals 5, the radius is 30. So that's also important. At t equals 5, the radius is 30 feet. So I'll mark that down. R of 5 equals 30. Okay? Now, we want to estimate the radius of the balloon when t equals 5.4 using a tangent line approximation. I will very, very briefly go over what a tangent line approximation is, in case you've forgotten. Okay, so if you have a graph, okay, and this is going to be the graph of t here and r of t here. We know that r is concave down, right? So maybe it'll look something like this, okay? Something like that. So we know that at 5, the volume is 30, or sorry, the radius is 30, right? At 5, let's say this is 5, the radius is 30, okay? And we want to know, what about at 5.4? What's going on there? But we don't know what the equation of r is, so we can't just plug in 5.4 into an equation. Right? So we want to find whatever this value is. We want to find that point, okay? We have this point, we want to find that point. Well, we can't figure this out, but what we can do instead is take this point, the yellow point, find the tangent line to it, like that. Whoa, let's draw that a bit better. The tangent line right there. And then we can find this point at 5.4, and we'll say, okay, these are close enough together. The green point is an approximation for the blue point. And that's what a tangent line approximation is. So what we're going to do now is we're going to find this green point. And to do that, we need the pink line. How do we find this pink line? Well, we need two things. First, a point, and second, the slope. Okay, so the point is, we need any point on this pink line. Well, we know that this point is 5:30, 5,30, right? So that's a point on the line. And then the slope of the line, the slope of the line, that is the derivative of r at t equals 5, right? What is the derivative of r at t equals 5? What is r prime of 5? Well, if we go to the table, we see that r prime of 5 is equal to 2. So the slope is 2. Now, putting these two bits of information together, I can write an equation for the pink line using point-slope form. It's going to be y minus 30 equals 2 times x minus 5. Okay? And all I have to do now is, if I want to find out what the green point is, all I have to do is plug in 5.4 in for x. So y is equal to 2 times 5.4 minus 5 plus 30. Okay? And then let's see, 5.4 minus 5 is 0.4, times 2 is 0.8, plus 30 is 30.8. Okay? And then simply for the units, we want to find out what the radius is, right? We want to find the radius at t equals 5.4. Well, they're measuring the radius in feet, so our answer is going to be also in feet. Okay? And then part B, or not part B, sorry, but like the second part of part A, asks, is this less than or greater than the true value? Well, you can easily see that this approximation is above the actual value, right? It's an overestimate. So our estimate is greater than the true value. And the reason for that lies in concavity. Okay? So we're given that r is concave down. Because r is concave down, the tangent line is always going to lie above the graph. And therefore, any estimation that we make using this tangent line is going to be an overestimate. On the other hand, if r were to be concave up, then the tangent line would lie below the graph, and any estimate made using that made using that tangent line would be an underestimate. But in this situation here, it's an overestimate, so that is why our estimate is greater than the true value. So if you'd say, okay, it's greater, and then the reason would be r of t is concave down for t between 0 and 12, okay? In terms of points, this was 2 points, 1 point for correctly getting the 30.8 feet, and the second point for saying it's an overestimate because of the concavity. Part B, find the rate of change of the volume of the balloon with respect to time when t equals 5, and indicate units of measure. Okay, so we know that the volume of the balloon is V, right? The volume is V, and we want to find the rate of change of the volume of the balloon. So we want to find how much the volume of the balloon is changing with respect to time. So that's dv dt, and when t equals 5. When t equals 5. Okay, that's what we want to find. Okay, and let's quickly make a list of everything we know about what's going on in this situation when t equals 5. When t equals 5, what's going on? Okay, well, we know two things. First of all, we know that the radius is 30 feet when t equals 5, right? So we know that r equals 30. Secondly, we know that the derivative is equal to 2, because when t equals 5, you can see here r prime of t is equal to 2. So r prime, which by the way is also equal to dr dt, is equal to 2. Okay, now that we know that, let's move on to actually finding dv dt. So we know that the volume is 4/3 pi r cubed, right? If we want to find the dv dt thing, then we can just take this equation and take the derivative of it with respect to time. So on the left side, we'll just get dv dt. And then for the right side, we'll take the derivative of this normally. 4/3 pi times 3r cubed, or 3r squared, sorry, by the power rule. But now since r and t are different variables, we'll have to add a dr dt on the end, because it's an implicit differentiation question. Okay, we can simplify this normally, the 3's will cancel, and we'll get 4 pi r squared dr dt. Okay, and this, we're saying that dv dt is equal to this. Now, we want dv dt when t equals 5. So, dv dt when t equals 5 equals, so 4 pi. And then what is r? What is the value of r when t equals 5? Well, to figure that out, we can go up here and say when t equals 5, we said r is equal to 30, right? So I can plug in 30 in for r. And then dr dt. What is dr dt? Well, I said it's equal to 2, right? So 2. 4 pi r squared dr dt. So this is the answer, but they also want us to include units, right? So how do we get the units? Well, let's see. Since the units for volume are feet cubed, right? Because the radius is in feet, and then the volume is feet cubed, and the units for time is seconds. Or sorry, no, time? No, it's minutes. So the units for volume are feet cubed. The units for time are minutes. Since we're dividing volume by time, the units for this are going to be the units for volume, which are feet cubed. That's an ugly F. Hang on. Feet cubed, which is the units for volume, divided by the units for time, which are minutes. Okay, so feet cubed per minute. And there is the answer. Okay, so this is a 3-point question. 2 points for successfully taking dv dt implicitly, and then 1 point for plugging in 30 and 2 to get your final answer. Part C, use the right Riemann sum with the 5 subintervals indicated by the data in the table to approximate this integral, and explain what it means in terms of the radius of the balloon. Okay, so let's quickly make a sketch of r prime of t. Okay, and by sketch, I don't mean a perfectly drawn graph, I mean a very, very rough sketch. So of t and r prime of t. Okay, and then from our table, it looks like we have 5.7, 4, 2, 1.2, 0.6, and 0.5 as t goes up. So I'm going to assume it looks something like that. Sure, not perfect, but it's good enough. Okay, now let me mark the t values. This is 0, this is 2, this is 5, this is 7, this is 11, and this is 12, right? So since we're doing the right Riemann sum, oh, also before we do that, actually, let me quickly talk about what they mean by 5 subintervals, okay? So the first subinterval goes from t equals 0 to t equals 2. The second goes from t equals 2 to t equals 5. The second goes from 5 to 7, 7 to 11, and then 11 to 12. Those are the 5 subintervals, okay? And then for each of those subintervals, you can see here we have the same numbers down here. If we want to find a right Riemann sum, we'll take this first group of subinterval, this first group of numbers in the subinterval, 0 and 2, and we'll take the right one, and that right one, let me draw it better, sorry. The right one will be the height of the rectangle, like that, okay? So 2 marks the height of the rectangle. In the second subinterval, from 2 to 5, 5 will mark the height of our rectangle, like that, okay? And then here, 7 will mark the height of the rectangle, and then 11, and then 12, okay? If we were doing left subintervals, this height here, the left height, would mark the height for our rectangle. So if we're doing left, it would look something like this. Okay, but we're doing a right subinterval, so we're using this height here. And basically what we're going to do now is we're going to add all of these up. We're going to add 1, 2, 3, 4, and 5. We're going to add these up, and we're going to say this is the approximate interval from 0 to 12. It's the approximating this entire area. It's not perfect, but it's an approximation, right? That's really what this is, Riemann sum. Okay, so now to find out this first red rectangle, we have a base of 2 and a height. And to figure out the height, we see, okay, so 2 is giving us the height, right? What is r prime of 2? Well, let's see here. At 2, we know the height is 4, right? So this point here is 4. The height is 4. So this area is going to be 2 times 4. Similarly, this distance here is 3, because between 2 and 5 is 3. And the height is this height at 5, which is 2. Here the difference is 2, and the height is 1.2. I can keep on going for the next 2. And if you were to add all these up, you would get 19.3, okay? And then for the units, it's going to be very simple, because for integrals, the units are simply the units for these axes multiplied together. So t is measured in minutes, and then r prime of t is measured in feet per minute, so multiplied by feet per minute. And you can see the units, the minutes will cancel out, and the units are just feet. So 19.3 feet is the answer here. Okay, and we also want to know what this means in terms of the radius of the balloon, right? So we just approximated the integral from 0 to 12 of r prime of t dt, right? Using the fundamental theorem of calculus, I can say this is equal to r of 12 minus r of 0. And what this really is, this is actually just delta r from 0 to 12, right? It's how much the radius changed from 0 to 12. So what this 19.3 represents is the approximation for delta r from 0 to 12. So we're approximating how much the radius changed from 0 to 12, the change in the radius. Okay, and we can actually knock out part D right now. Is the approximation from part C, which is 19.3, greater than or less than the actual value of the integral from 0 to 12 of r prime of t dt? Give a reason for your answer. Okay, well, let's see here. So we know that r prime of t is decreasing, right? And we especially know that because r is concave down. So since r is concave down, r prime of t is decreasing. And then you can see here, since r prime of t is decreasing, all of the right subintervals, all these rectangles, they're leaving this little extra tidbit of space, right? So the actual value would be more, because when we do our rectangles, we're not accounting for these little pink spaces. So the actual value is more than 19.3 feet, but our subintervals are missing these bits. So the reason we're not including these is because our approximation is an underestimate, since r prime of t is decreasing. Okay, so is our approximation for t less than or greater than? Our approximation is less than the integral, and the reason is that r prime of t is decreasing. So let's see, for part C, that was a 2-point question. 1 point for this correct Riemann sum, 1 point for the correct answer and the explanation, the one along with it. Oh, no, sorry, no, my bad, sorry. You get 1 point for the correct answer, and 1 point for the explanation about how it's the change in radius from 0 to 12. And then for part D, it's simply a 1-point question for the correct answer and explanation. And for parts B and C, where they asked you for units, remember in part B it was cubic feet per minute, and in part C it was just feet. If you got those both, then you'd get an extra units point. That was the end of question 5. Question 6, final question. Let f be the function defined by f of x equals k square root of x minus natural log of x for x is greater than 0, of course, where k is a positive constant. In part A, we're asked to find f of x and f double prime of x. Okay, so let's start with f prime of x. Okay, remember, k is a constant, it's not a variable here. So we want to find the derivative of this. We'll take it this part and then this part. Okay, so first we'll take this part, the derivative of k square root of x. Well, let's see, you should probably, this might be something to memorize, it's a lot easier. The derivative of the square root of x is 1 over 2 square root of x. So here, the derivative of k square root of x is k times 1 over 2 square root of x. Okay, and then minus natural log of x. So the derivative of natural log of x is 1 over x. Okay, so here, this is f prime of x. We took the derivative of this here, and the derivative of this here. Okay, that's f prime of x. There you go. And then for f double prime of x, it's the derivative of f prime of x, right? So let's see here. This one we might have to do a bit more thinking, right? So let's take this here. So we have k over 2 square root of x, right? This is equal to k over 2 times x to the negative 1/2, right? So what we'll do, if we want to take the derivative of this, we'll take the 1/2, bring it down here, and we'll subtract 1, right? So if we bring the 1/2 down, we'll get negative k over 4, right? Because the negative 1/2 times this k over 2 is negative k over 4. And then x 1/2 minus 1 is negative 3/2. Okay? And then for the minus 1 over x, minus 1 over x is negative x to the negative 1, right? So if we want to take the derivative of this, we'll take the negative 1, bring it down here, and subtract 1 again. So if you bring the negative 1 down here, we'll have the two negatives, we'll cancel to make a positive, and then we'll get x to the negative 2, which I'll write as 1 over x squared. There's f double prime of x. Okay? So this is a 2-point question, 1 point for each derivative. Part B, for what value of the constant k does f have a critical point at x equals 1? For this value of k, determine whether f has a relative minimum, maximum, or neither at x equals 1. Justify. Okay, so remember, what the critical point means is that the derivative is 0 or undefined, right? And x equals 1, we'll plug in x equals 1 into here for f prime of x. F prime of 1. We're going to say that's equal to 0. Okay? So, what is f prime of 1? We'll plug in 1 into x, we'll get k over 2 square root of 1 minus 1 over 1 equals 0, right? This is f prime of 1. These two are one and the same. And we're setting them equal to 0, right? I'm asking what value of k does this equal 0? So we'll simplify this a bit more. This will simplify to k over 2 minus 1 equals 0. That's going to just mean k equals 2. Okay? Nothing really crazy there. And they also want us to say, for this value of k, determine whether f has a relative minimum, maximum, or neither at x equals 1. Justify your answer, okay? So to determine whether we have a relative minimum, maximum, or neither, we're going to pull in the second derivative test, okay? Second derivative test says we plug in these numbers into the second derivative and then see what happens to the sign of the answer. Whether it's positive or negative, we'll determine whether we have a maximum or minimum. If the second derivative comes out to be equal to 0, then we have no clue. So let's find the second derivative at 1. Okay? So let's see, we know k is 2, so I can plug in negative 2 over 4. Okay, and then I'll plug in 1 in for x. Plus 1 over 1 squared. Simplify that to negative 1/2 plus 1. which is 1. Okay, 1 is obviously a positive number, it's greater than 0. And by the second derivative test, if the second derivative is greater than 0, so it's positive, then f has a relative minimum at that critical point. So at x equals 1, f has a relative minimum by the second derivative test, since the second derivative is greater than 0. Okay, so they asked us to justify our answer. We justified it using the second derivative test. So this was a, let's see here, this was a 4-point question. 1 point for setting f prime of 1 equal to 0. 1 point for getting the right k value. 1 point for stating that f has a relative minimum at x equals 1. And another point for the justification by the second derivative test. Part C, for a certain value of the constant k, the graph of f has a point of inflection on the x-axis. Find this value of k. Okay, so this one was a little bit tricky because they snuck this little thing on the end on the x-axis, okay? And that meant all the difference. So we know two things, all right? There's some value of the constant k, and there's a point of inflection for f, and it's on the x-axis, okay? Those two different bits, point of inflection and x-axis, they give us two different pieces of information, okay? So the first bit of information, the point of inflection, means that the second derivative is going to be equal to 0. So when the second derivative is equal to 0, that's when we have an inflection point. So I'll say that f double prime of x equals 0, okay? Actually, let me do it in orange. Okay? And then on the x-axis, well, if something is on the x-axis, that means its y value is 0, right? So that means f of x equals 0. So we know that at this k value, we know that f double prime of x equals 0 and f of x equals 0. So we need to find some value of k that makes both of these things equal to 0, okay? So we'll start one at a time. We'll start with f double prime of x, okay? We'll take this guy and set it equal to 0. So negative k over 4, x to the negative 3 over 2, plus 1 over x squared equals 0. And by the way, something important, x is greater than 0 here, right? So, yeah. I can bring the 3 halves down, so I'll get negative k over 4x to the 3 halves plus 1 over x squared equals 0, okay? And I will multiply everything here by x squared. That'll simplify a lot. And that will get us, let's see here, so on the right side, 0 times x squared is 0. On this side, we'll get negative k x squared over 4x to the 3 halves plus, okay, so this and this are going to cancel. We'll just get 1 equals 0, okay? And then when we have an x squared and we have an x to the 3 halves, we can simply subtract these exponents, right? So it's going to be negative k x to the 2 minus 3 halves is just going to be x to the 1 half over 4 plus 1 equals 0, right? I can simplify this a bit more. I'll subtract 1 and get rid of the negative and multiply by 4. That'll get us that k times the square root of x, because x to the 1 half is square root of x, equals negative 4, or sorry, equals positive 4. Equals positive 4. I subtracted 1, then I cancel the negative, so I get kx squared, sorry, k times the square root of x over 4 equals to 1, and then I multiply both sides by 4, and I get k squared of x equals 4, and then I can solve this and I'll get k equals 4 over square root of x, okay? Now let's do the same thing for the second part, f of x equals 0, right? So we know that f of x equals k square root of x minus ln x. So we know that k square root of x minus ln x equals 0, okay? So I'll add ln x to both sides and divide by the square root of x to get that k equals ln x over square root x, okay? So we know that at this k value, we have k is equal to 4 over square root of x, and k is equal to ln x over square root of x, right? So since these are both equal to k, I'll set these two equal to each other, and I'll get 4 over square root of x equals ln x over square root of x, right? these are both equal to the same thing because they're both equal to k. So we'll set them equal to each other, right? The square root of x will cancel out, and I'll get ln x equals 4. I'll put an e as the base to both of these. That'll get me these canceling out, and I'll get x equals e to the 4th. Okay? And since k is equal to 4 over the square root of x, k, let's do it again, k is equal to 4 over the square root of e to the 4th, which is 4 over e squared. That's the value of k. And remember at the very beginning of the question they asked us, find this value of k that makes this stuff be true. Okay? And then let's see, for this question, this was 3 points, okay? 1 point for stating that either one of these was true. You didn't have to state them both. You either had to say f of x equals 0 or f double prime of x equals 0. You had to state one of those to get a point. And then you had to have an equation with one variable. And in our case, that was this equation down here. We took these and we got rid of the k variable by setting these equal to each other. That allowed us to solve for x, remember? So we got another point for setting these equal to each other and having an equation with one variable. And then the third point for finding the correct value of k at the end. That concludes this 2007, I think, right? 2007 AP Calculus AB exam. I hope you found this review helpful, and I will see you in the next video. Goodbye.